Hello students, today we will start our second unit, that is current electricity or electric current. Electric current denoted with symbol I. It is said to rate of flow of charge is called current. Whenever charge flows in a conductor, it is called current, denoted with I equals to Q over T or dQ over dt. Q is used for charge and T for time. d over dt is representation of first derivative, that is rate of change with respect to time g. So charge flows in various materials called conductor, which allow to flow current. Conductor are simply classified into two types. First one are the metallic conductors, and second one are electrolytic conductors. Metallic and electrolytic conductors. Metallic conductors are generally in solid form, example copper, iron, aluminium, etc. And electrolytic conductors are in a liquid form or aqueous form, like aqueous HCl, tap water, aqueous NaOH, etc. are the examples of electrolytic conductors. Metallic conductor consist of free electrons, due to which electric current flows in metallic conductor. These consist of free electrons. Whenever a charge moves, means free electrons moves in a conductor, due to which electric current flows. Whereas in electrolytic conductor there are ions, free ions, which are free to move in that aqueous solution or liquid. Ions like positive and negative charged particles, cations and anions, moves in electrolytic conductors. So next we will watch next is motion of charge carriers. Motion of charge carrier, that is which represent actual direction of flow of current. Charge carrier, there are two types we already discussed, that is electrons and ions. Here we study only metallic conductor, that is electrons. Consider we have a metallic conductor which is connected to a cell. These positive and negative symbol represent two terminals of cell, and electron will move from negative terminal of cell to positive terminal of cell. So charge will flow due to flow of electrons. Electron move from negative terminal to positive terminal of cell through a conductor. Because electron consists negative charge, and negative charge will move from negative terminal to positive terminal. In a conductor, the direction of electron in such a way that it represent direction of current. So actually, if we have to represent a direction of electric current, that will be electron moves in a conductor. Electron moves from negative to positive terminal. So direction of electric current is actually positive to negative terminal of cell, or we can say positive, which is at high potential and negative which is at low potential. So actual direction of electric current is opposite to direction of flow of electrons. It is similar to like we have a water tank at certain height and water will flow from that height towards the earth. Similarly, electric current flow in a conductor from positive to negative terminal. As we have already discussed, positive terminal is considered at high potential and negative terminal is considered at low potential. So electric current flows from high potential to low potential. So this is about direction of flow of a current. This direction is also called conventional direction of current. So current is a scalar quantity. That means electric current has not specific direction. It has only magnitude but no direction. The quantities which have only magnitude but no direction are called scalar quantities, whereas the quantities have direction as well as magnitude are called vector quantity. Electric current is considered as a scalar quantity. So I equals to dq over dt. So here we will find units of electric current. Electric current units are ampere, charge units are coulomb, and time units are second. So ampere, 1 ampere equals to 1 coulomb over 1 second. So these are the SI unit of electric current. SI unit of electric current are ampere, electric current ampere, and charge coulomb, and time SI unit are second. So 1 ampere can be considered as a coulomb per second. Whereas dimensional formula for electric current is, we have no other quantities needed to calculate dimensions for electric current. So here m will be 0, mass no required, length 0, time 0, a only a, that is dimension of electric current, a1. So simply dimension can be represented as similar to units symbol a. So next we will start our first topic, drift velocity. Topic name is drift velocity. Consider we have a metallic conductor connected to a cell having electric field E, in which when potential is applied, electron will start moving from negative terminal to positive terminal in a conductor. Whenever there is no electric field is applied, means no cell is connected or no external potential is given to our conductor, then their electrons average velocity will be 0, that is u1 plus u2 up to un over n equals to 0. u1, u2, un, these are the initial velocities of electrons. These velocities will be due to thermal motion. Total average velocities will be 0. consider this equation number 1. As we already know, F equals to ma, where F is force, m mass, and a acceleration. And similarly, F equals to E into E, where small e represent charge on electron and capital E represent electric field. From these two, we calculate A equals to minus E over m, E over m, where negative sign represent charge on electron, which is negative. So this is our first important result. Now, when we apply potential to the cell, then the average velocity of electron is considered as drift velocity of electrons. When we apply potential to that conductor, the average velocity of electrons is called drift velocity of electrons. So Vd, representation or symbol of drift velocity. So this is the definition. Average velocity of electron under the influence of electric field is called drift velocity of electrons. As we know the equation of motion, v equals to u plus at. V is final velocity, u is initial velocity, a acceleration, and t is time. So final velocity of first electron v1 equals to u1 plus at1. Similarly, v2 equals to u2 plus at2, and so on. vn equals to un plus atn. The acceleration for each particle or electron will be same, because as we already deduced, acceleration equals to minus e over m. So drift velocity equals to v1 plus v2 up to vn over n. This is the exact definition of drift velocity. So here we will put the value of v1, v2, v3, vn, so on. So Vd equals to u1 plus at1 plus u2 plus at2 up to un plus atn over n. So here the simple steps: Vd equals to u1 plus u2 up to un over n plus a t1 plus t2 up to tn over n. Here we separate the LCM of above equation. So our result is as, so Vd equals to u1 plus u2 plus un over n is 0, initial velocity, a into t1 plus t2 up to tn over n is simply considered as tau. So Vd equals to a into tau, where tau is called average relaxation time. This is called average relaxation time. Simply t1, t2, t3, tn over n. What is this average relaxation time? In a conductor, when electron moves from one side to another, these moves by colliding with each other. So time taken by electron between two successive collisions, is called relaxation time or average relaxation time. So our Vd equals to, now we will put the value of a, that is minus e tau over m. So here we put the value of a, or simply we can write as Vd equals to q e tau over m, where q is symbol for charge as vector form. Vd, drift velocity, is a vector quantity, and electric field intensity is also a vector quantity. So this is our end result or expression for the drift velocity. Vd equals to q